All right. Hopefully you had an opportunity to play with the optical light box yesterday. So I'm trying to model this way things refract through an object. But I'm going to be explicit today. Here's how you do it, step by step. First off, you draw a normal line to the surface. Thanks. Okay. Then draw the path of no refraction. And then answer the question, does it bend away from or towards the normal line? And you're looking specifically at this normal line. Going from air to glass, it's going to go from low index of refraction to high index of refraction. Is going from fast to slow. It's going to bend towards the normal line. So then draw it as so. Good with that? I'll do it again. Normal line, no refraction, and then answer the question, bends away from or towards. In this case, going from glass to air, it's going to bend away from. So it's bending away from this normal line here. Good? Okay. On this one, the bottom one is going to do the same thing. Boop, boop. It's going to cause those two rays to intersect. Okay. Do you see how this lens has a similar construction to these two prisms, similar arrangement of these two prisms? It's thick in the middle, it's skinny on the top and the bottom. Good with that? So when parallel light rays go through, what's going to happen is they are going to intersect. It's made in such a way that they intersect at a certain point, known as the focal point. Okay, so when parallel rays go through, they intersect at the focal point. Through that. So if we were to take parallel rays going the opposite way through there, in this class, it's going to be designed in such a way that they're going to intersect, and this focal point, or this focal length, and this focal length are always, in this class, going to be the same. It's going to be made symmetric. This is not necessarily how it works in real life, but in this class, the focal lengths are always going to be the same. Distance away from the lens. Good with that? Okay. This is known, this type of lens is known as a converging lens. Known as a converging lens. Okay. That makes sense with the why it's called converging. Okay. Okay. there are two different ways to figure out what an object's going to look like if seen through a lens. The first way is through ray diagrams. Okay, so if you're taking notes and you don't have the slides printed out, a really important detail is the fact that this focal length needs to be equal to this focal length in order for this to work. Okay, so like use a ruler, use like knuckles on your finger to like make sure that these like those distances are the same. Okay. So this is the object. This is the principal axis. This is the focal point, and this is the focal point. So principal axis, focal point, and focal point. Okay. Do not copy this next thing down. Do not. Okay, so light is reflecting off of all parts of this object. I only care about the top part. Okay, and light is reflecting in all directions off the top of this object. Okay, in all directions. Everybody good with that? I only care about 3 of those rays. Okay, so now you can start copying what I'm doing here. First ray, you always start at the top. Okay, and it goes parallel to the principal axis. Using a straight edge is helpful. It's going parallel to the principal axis. Okay. And then when the light goes through the lens, how will it refract? How will it bend? It is going to go through far focal point. Through the far focal point. Good with that? Most people don't have a problem with that one. That kind of corresponds to what we just talked about here. Okay. Now, the second one's a little bit tricky. Let's pretend that we had a laser and we're going to shine it through this focal point this way. How's it going to refract? How's it going to bend? Okay. If it was coming in parallel, then it would refract through this. But this is not coming in parallel. It's actually going to reverse this same path and go parallel. You right with that? Okay. Okay. So here's what we're going to do. We're going to always start at the top of the object, and we're going to go through the near focal point. Okay, so it goes through the near focal point. And because it goes through the near focal point, how will it refract? How will it bend? Tell your neighbor what you think. It will refract parallel to the principal axis. Parallel to the principal axis. Good with that? Last ray, in my opinion, is the easiest. It's my favorite. What we're going to do is start at the top of the object. And we're going to go through the center. Okay, now, here's the idea here. Any light that comes into or out of the lens above the principal axis is going to bend it like down, like it's bending it somewhere this way. Any light that comes into or out of the lens below the principal axis gets bent sort of up. Well, check this out. It goes in above the principal axis, bends down, comes out below the principal axis, bends up. If this is thin enough, then we can approximate that, just go straight through. And that's what we're going to do every time. This is like thin lens approximation. Okay, so we can say it goes straight through the center. No refracting, just and hopefully you drew it correctly so that all three intersect. Good with that? Where they intersect, this is the top of the image. The bottom of the image is still on the principal axis. So how is it that the top of the image could be below the principal axis, but the bottom of the image is still on the principal axis? It gets flipped. It is upside down. So this is your image. So we could describe that image, a couple characteristics. Is it upside down or right side up? Upside down, we call that inverted. Is the object, is the image bigger or smaller than the object? Smaller. So we say it is shrunken. And the third characteristic, which we'll talk about here in a second, is it is real. What does that mean? That means the light rays actually intersect. When the light rays actually intersect, we say that is a real image. Good there? So this is when an object is far away from the focal point. And the object is far away from the focal point. This is what that ray diagram looks like. It will produce an image that is inverted, shrunken, and real.
The object's on the focal point. Next.
Nope. Worksheet. Great question. Okay. All right. Next scenario is when the object is closer than the focal point. So go ahead and, if you're taking notes, go ahead and reconstruct that. Make sure your focal lengths are equal distance away. And go ahead and draw the first ray. Thumbs up when you've drawn the first ray. Parallel to the principal axis and through the far focal point. Okay. Now the second one gets a little wonky because we need to draw through the near focal point. But when we draw through the near focal point, it's like, whoop, totally missed the lens. Like, what is up with that? So what we do is we say, well, let's say a ray of light went through the near focal point, through the top of the object. So we line this up like this, and then draw from the top of the object. Does that make sense how we cheat that? And then that refracts parallel. The third one goes through the center. Oof. There he is. What do you notice happens to the rays, the refracted rays, or what doesn't happen, more specifically. They don't intersect. Oh, what do we do? So if rays don't intersect, then draw the refracted rays backwards. If the rays don't intersect, then draw the refracted rays backwards. So, of these two, A or B, which one is refracted? The refracted ray, A or B? A or B is the refracted ray. B is the refracted ray. So we're going to extend the refracted ray backwards. Okay. Which one is refracted? A or B? A or B? A or B? B is refracted. So I'm going to extend that backwards using a straight edges. Oh, sad day. Even with a straight edge. Get it. That's a sad state of affairs here. Okay. And then the blue one's easy. It's just a straight line. So extend that backwards. And the hope is they all intersect at the same point. And this would be the top of your image. So you would describe the image how? Upright or inverted? Upright. Shrunken or enlarged. And if it's not real, what we say is it is virtual. Okay. So if you have to extend the arrays backwards, this is a virtual image. Grab a lens, make sure it has a positive focal length. If it doesn't, just call me back. They should all have positive focal length. Grab a lens. Make sure it has a positive focal length. Make sure it has a positive focal length. Yeah. There's a sticker on it. The number should be positive. All right, so if you have if you look at this, winking with one eye and look at something far away, how do you describe the image? Hold the lens away from you as well. At arm's length, hold the lens, arm's length, wink. How do you describe the image? Upside down, shrunken, and here's how we're gonna demonstrate real.
Is it possible to make yourself not real?
The object. No. Okay, get out a piece of paper. I'm gonna pretend to be you. Sitting here looking at the board. I'm gonna swing my legs so they're facing this way. Everybody do it. Okay. You're gonna take a piece of paper. You're gonna hold it in your left hand like this. Take a piece of paper with your left hand. Take the lens with your right. Okay. And you're going to not look through the lens, but you're going to move the lens back and forth until you see something on the paper. You're not looking through the lens, you're just looking at the paper. You will know when it happens. Okay? Move it back and forth until you find it. How would you describe this image? Upside down, shrunken, and the fact that you can project it on a screen is real. You cannot project virtual images onto a screen. Good with that? Is everybody seeing that? Okay. Okay, so here's far away. Oh, so awkward. Oh, this might not work for you guys. Sorry. Multiple lenses. I don't know if that works. Let's see if the flag's upside down. Shoot. Ignore this. It doesn't work. Sorry, kids, in the video. Multiple lenses. Oh, maybe it did. Yeah, it did. It did. Good. Okay. So that's that. And then here's the trick. Oh, this is going to be awkward. Let's see how this is going to work. Your eyeball's going to be doing that. It's not as cool when I'm not sitting there swinging my arm. There it is. Anyway, there's an image on there. You can't see it. Sorry. All right, moving on. Here come the lights. Pass this around. If you could put those back in there. Okay, next type of lens has a similar effect to two prisms arranged like this. Okay, it's going to refract and refract, refract, refract. Okay, does everybody see the similarities with these two, the arrangement of these two prisms and this lens? Thick on the top and the bottom, skinny in the middle. Okay, this lens is going to cause light to go away from focal point. Okay, this is known as a diverging lens. It's a diverging lens. And it goes away from the focal point. Did you see that in the lab yesterday? Okay. All right, here's the ray diagram for a diverging lens. So, in general, for a diverging lens, the roles of the near and far focal points are swapped or flipped. I don't know what you want to call it. Again, if you're recreating these, make sure your focal lengths are equal distance away from the lens. Okay. So ray number one, parallel to the principal axis. If this was a convergent lens, then it would refract through the far focal point. But because it's a diverging lens, it's going to refract as if it was coming from the near focal point. Okay. The next ray, if we had a laser going in, pointed at this opposite focal point, it's going to refract parallel. So what we're going to do is the same idea. We're going to go taking our straight edge from the top of the object to the far focal point. The far focal point, and then when it goes through the lens, it's going to refract how? going to refract parallel. Last one, my personal favorite. I'm going to go straight through. Do the rays intersect? Nope. So go ahead and figure out where the image is going to be and how you would describe the image. I don't have enough divergent lenses for everybody, but one per row. So look at something far away. You can look at it close, it's just not as distinct. And see if your ray diagram matches. If you're waiting on the lens, go ahead and finish your ray diagram, figure out where the object is going to appear and how the characteristics you would use to describe it.